conditions must be met for a gasoline internal combustion engine to run at maximum efficiency. There must be a good air-fuel mixture, a high level of compression, and an ignition system which has optimal timing and powerful sparks. Optimal ignition timing and powerful sparks are the responsibility of the ignition system. There are various types of ignition systems. In this video, we will mainly use a fully transistorized ignition system to explain the functioning of the ignition system. In this video, we will look at first, the structure of the ignition system. Second, how a high voltage is generated. Third, control of ignition timing. Fourth, spark plugs, which use the high voltage to emit sparks, igniting the air-fuel mixture. Fifth, other ignition systems. And finally, inspection and adjustment of the ignition system. In a gasoline engine, spark plugs ignite the compressed air-fuel mixture and generate combustion, providing power. So the ignition system must be able to produce a high voltage in order to provide optimal ignition timing according to the engine's operating conditions. First, let's take a look at the components of the ignition system and their function. Electrical power is provided by the 12-volt battery. The ignition switch. The ignition coil and igniter convert the battery's low voltage into a high voltage. This is relayed by the distributor to each cylinder's spark plug. This distributor incorporates an advancer device to obtain optimal ignition timing. A distributor with a built-in ignition coil is called an Integrated Ignition Assembly, IIA. The charge from the ignition coil creates a spark at the spark plug, igniting the air-fuel mixture. Spark plugs require a high voltage of more than 10,000 volts to generate sparks, but as we have seen, the vehicle's only source of electrical power is a 12-volt battery. So how do we generate a high voltage from a 12-volt power source? Let's explain. Take a look at this experiment. A 100-volt lamp is connected across the battery and the switch is turned on. The voltage is only 12 volts, so the lamp doesn't light. Next, a coil is connected across the lamp and the circuit switched on once more. Once again, the lamp fails to light. But at the instant the switch is turned off, the lamp flashes. Here's why. If the switch is turned off when current is still flowing in the coil, a large electromotive force, EMF, or voltage, is generated, flowing in the opposite direction. This is called the self-induction effect, and the electromotive force generated is called the counter-electromotive force. Next, let's do another experiment. Two coils with different thicknesses of wire and numbers of windings are connected in series. The moment the switch is turned off, the flow of current in the primary coil is cut, generating a greater current in the secondary coil. Current is switched on and off in the primary coil, a high voltage is generated in the secondary coil. This is called the mutual induction effect. An ignition coil integrates these two coils into one. Let's conduct a test with an actual ignition coil. The current flowing in the primary coil is turned on and off. As you can see, the ignition coil uses the self-induction and mutual induction effects to generate a high electromotive force of tens of thousands of volts from the 12-volt power source. Conventional systems use conductive breaker points in the distributor to turn the switch on and off mechanically, just like this device. But today, most systems make use of the switching effect of a transistor or an electronic control unit, or ECU. Now let's take a close look at how a high voltage is generated using an actual transistorized ignition system. An ignition coil, a signal generator, and an igniter are integrated with the distributor. In the transistorized ignition system, the ignition signal from the signal generator is transmitted to the transistor in the igniter. This transistor turns the primary current in the ignition coil on and off. The signal generator has three components: a signal rotor, which makes one turn for 2 revolutions of the crankshaft, a pickup coil, and a permanent magnet. The rotor turns clockwise or counterclockwise depending on the engine. As the rotor turns, a voltage is generated in the pickup coil. This is the ignition signal. But why is a voltage generated? The magnetic flux of the permanent magnet flows through the signal rotor, the pickup coil, the bracket, and returns to the magnet. When the rotor is still, there is no change in the magnetic flux. When the signal rotor rotates and a rotor tooth approaches the pickup coil, the magnetic flux density increases. As the rotor tooth moves away from the pickup coil, it decreases. This means that the voltage generated in the pickup coil depends on the changes in the magnetic flux. The level of EMF generated depends on the relative positions of the rotor and pickup coil. When a rotor tooth approaches the pickup coil, the EMF increases. And when the rotor tooth and the pickup coil face each other, it becomes 0. When they move apart, a counter EMF is generated. These changes in the EMF cause the igniter to switch the primary current on and off. Let's take a look at how the current is turned on and off. When the engine is running and one of the signal rotor's teeth approaches the pickup coil, the voltage is generated in the direction shown in the diagram. The base current flows in the transistor switches to on, and the primary current flows in the coil. When the signal rotor's tooth is aligned with the pickup coil, the voltage generated in the pickup coil decreases and the transistor is turned off. This cuts off the primary current and generates a high voltage in the secondary coil. The transistor is also turned off when the voltage is generated in the opposite direction in the pickup coil. In this way, when the engine is running, the transistor is turned on and off every time one of the signal rotor's teeth passes the pickup coil. Every time the transistor is turned off, a high voltage is generated in the secondary coil. The voltage generated in the secondary coil then passes from the distributor's center electrode through the rotor and from the outer electrode to the spark plugs, according to the firing order of each cylinder.